Okay, YouTube, in this video I'm just going to work through solving a quadratic, it seems, inequality here, but a nonlinear inequality and kind of the process you go through here. So the first thing I want to do is actually we want to get the right side to have a 0 on it, because if we can get this 9 back over here, then we would have the expression x squared plus 4x minus 5 is greater than or equal to 0. But what we could do is we could really interpret this as being some function of x or some set of y values that are dependent upon these x values here. And what we're really asking is, what are the x values for which our function happens to have greater than or that our y values are greater than or equal to 0. So what we could do is kind of cheat in this video a little bit before we move forward, talk about the process here. What we'll do is we'll take a look at the graph here, and what I've done is actually got 3 functions in here, but this third one turned on as this x squared plus 4x minus 5. Let's go take a look at its graph. And basically what I want to point out is this. We're saying that this is some function of x here. We want to know where the function value is greater than or equal to 0. Well, that would be anywhere that we have positive y values on this graph. So I notice that this is some parabola that crosses at these 2 zeros right here and has positive y values here and here. So really what we're trying to do is find the intervals on the x-axis that we have those positive y values there. And so, looking at it this way, I suppose we could head over to a better graph in Desmos. I also did graph this here. If I were to say now greater than or equal to 0, I believe this will do it for us here. But why don't we leave this graph? I'll copy and paste the whole thing in again. So Control C, Control V. And what we'll do this time is we'll write greater than or equal to 0. And you'll notice here that I hope that it kind of colors the x values to the left and to the right of these 2 x values here that are zeros, because these are where we have positive y values. So what we really want to indicate is this. When we're solving one of these, we want to get 0 on the right hand side, but we're saying if that is so, then really the only place where this function can go from being positive to negative is at a 0. So we need to start by finding our critical values here. We can already see the intervals that are going to solve this, but that'll be good as a foreshadowing tool here. So one, we're going to find our critical values. It means the zeros of this. So if I find the zeros of this, means first of all we need to set it equal to 0. And I'll solve this by factoring. It's be really easy to do. I notice that it does factor. And so I suppose we'd have to have a positive 5 and a negative 1. And if those are the factors, then we'd say, well, then the critical values here in this case are negative 5 and positive 1. I'm going to write that here. We have critical values. And so what this does is it splits our number line up into our test intervals. So we say 0, 1, 2, 3, 4, and 5. And we'll go negative 5 here because that would be sufficient to go ahead and show what we need to show. But essentially our critical values, I'm just going to put a little x on the number line at each one here. We say there, and also at 1. I'll label that 1. We already know as we've graphed this that the solution intervals are going to be to the left of negative 5 and to the right of positive 1 on the x-axis, just by looking at the graph. And we could have said that right here, as a matter of fact. But what we need to do is split this number line up into our intervals. So we have negative infinity to negative 5 in union. Well, actually, we don't need to union anything yet. We just say these are our intervals, I suppose. And we say negative 5 to 1, and we'll say 1 to infinity. And so we say, which of these intervals solve the initial inequality? Well, we already know, looking at this, that it's going to be those 2 right there. But I do want to test this out. And what we'll do is we'll just choose a representative x value to plug in. So we say, well, negative 6 is on this interval. We could choose it and see if it makes it true. And plugging that into the initial expression here, what I'll say is it's a lot easier to use the factored expression. And so what we have here is we have this x plus 5, x minus 1. And if we're using this in the initial inequality sense, we said it's greater than or equal to 0. That's the same expression as what we started with here. You could see that if I were to put in a negative 6, I get negative 6 plus 5. And negative 6 minus 1 greater than or equal to 0. What I want you to see is essentially we would get here a negative. I guess it doesn't even matter. We just get a negative. And here I also get a negative. And a negative times a negative is a positive. So this is going to satisfy this initial inequality. So I'm going to put a big fat bubble around this. I'm going to say that's in our solution set. If we chose 0, we would have had like a 0 here and a 0 here. I just want you to see that this would have been a positive value. This would have been a negative value. And that would have been a positive times a negative is a negative. And a negative is not greater than or equal to 0. So this will not work. And of course, if we choose 2 here and test it, it's going to work. So this is also in our solution interval. So all we really need to do now is just color in our solutions and write our solution set. We would say negative infinity to negative 5 in union with 1 to infinity. And on the number line, we would say that it's these x values right here. So last thing I want you to notice is this. I'm using brackets. And the reason why I'm using brackets is because it could be also equal to 0. So when we're looking at this picture, we say, where are y values greater than 0? We say, well, for all of these x values here and here, but it's also or equal to 0, so we had to include the two zeros here, which are 1 and -5. Cheers.